So at ARPA-E, we felt that there was an opportunity for our technologies that had come from earlier projects and programs. There was a concern that they may be stranded, that they needed additional support to actually go from their lab stage to a demonstration phase. The goal of the scale-up program is to take technologies to the next level of demonstration, to start to prove out their value proposition and to demonstrate that they have the scaling capabilities, whether it's a product or a process. Natron was a very interesting technology and a very good candidate for scale-up, as the team had already de-risked their technology significantly during their original project. They had a very strong team that had a track record for scaling projects, scaling manufacturing. They also had some very good backing from a financial point of view, and also from a supply chain, and also from a customer base too.
Natron Energy has developed a sodium-ion battery technology. We store sodium ions in electrode materials based on Prussian blue pigments. And these batteries offer significantly higher power density, much longer service life, and unique safety characteristics in comparison to existing technologies. So ARPA-E brought the first money into Natron, even before our first venture capital seed investments. And with that first ARPA-E award, we were able to develop the core Prussian blue chemistry in our battery cells. Subsequently, we productized that technology, began taking it to market on a pilot line. And after seeing that progress in the markets and in the supply chain, ARPA-E then came back with this scale-up award. The purpose of this scale-up award is to support Natron in ramping from a pilot line to mass manufacturing. And it's more than an order of magnitude scale-up. And what that allows us to do is to go from serving one customer a month to dozens. And in the process of doing so, with all of the scaling, we're able to bring the cost of our technology down and prove that we have a viable business. For this interview, I'm actually sitting in a plant in Holland, Michigan, that was originally built for the purpose of manufacturing lithium-ion batteries. And it was originally built with DOE support. Natron is using this facility for the production of its sodium-ion Prussian blue technology. And ARPA-E's role through the scale-up program is to help us finance new equipment that will allow us to repurpose this existing plant for our new technology. In terms of what this means for our business, there are only a few plants in the world like this one into which we could bring a new technology very rapidly. ARPA-E has been unbelievably supportive, and everything we have, we owe to ARPA-E. We wouldn't have raised the initial venture capital funding round for Natron except because ARPA-E had brought the first grant and supported this technology concept. And similarly, the scale-up award from ARPA-E was a signal to prospective investors that the technology has legs, that it's been de-risked, that the pilot line works.
So for me personally, working with companies like Natron and other teams, awardees within the scale-up program, it's very exciting for me to see them come from the laboratory to the demonstration, the bench phase, all the way to a manufacturing environment like you see here today, that really shows the capability and the potential for maximizing the impact of our technologies at ARPA-E.
The most important thing I do in my career will be taking Natron's product to mass manufacturing and making a big market impact. And when we think about the problems we're trying to solve in society today, climate change is one of the fundamental issues. I can't think of anything higher impact that we should be working on.
Hi, good morning, everyone. Thank you all for coming this morning and spending time with us on this webinar. We are from Fuji Biodex. My name is Shen, and we are in partnership with Natron Energy to propose an alternative battery technology to you this morning. And we thank you for your time and your patience. So just let me go through a few specifics this morning. We will have a 40-minute presentation followed by a 10-minute FAQ. Due to the constraint of time and to make this efficient, we have to mute and everybody due to this process. Okay, but however, please do type your questions in the chat and we will answer them on a first come, first served basis as much as possible. which we will answer as quickly as possible as you can during the FAQ session. So we hope that you can type in, but if there are some questions you really need to ask personally, you can leave it to the FAQ after we try to answer all those questions. So today we try to introduce to you a new battery technology called sodium-ion technology from Natron Energy. We are in partnership with them to develop this technology and bring this to the markets of Southeast Asia. Therefore, today we are very happy to have Mr. Jack Pouchet, the Vice President of Natron Energy, and Mr. Brian Kenny, the Director of Marketing and Development, to bring us this topic of Natron's sodium ion and to let us understand more about this technology. So without further ado, I will just give another few more minutes to some people who still might be coming in, maybe 3 or 4 minutes, while we will hand over to Mr. Jack then. Please do take note that this presentation and this seminar will be recorded. So thank you very much for your patience, and we hope that you have a lot of questions for us later on. All right.
Thank you for that kind introduction, Shen, and my thanks to everybody behind the scenes at Fuji Brightex who are making this meeting possible and driving it today. Before I forget, I will be in Singapore in roughly 4 weeks at Data Center World, and really looking forward to meeting those of you who will be at that conference. So a little bit about Natron. You may think of us as a startup, but we've actually been around now over 11 years. Founded in 2012 as a spinoff from our founder, Colin Wessel's research work at Stanford on unique electrode properties for batteries, and that's what makes us able to do sodium-ion batteries today. So we're a little over 180 employees between Southern California, Michigan, a few people in Europe, and we're looking to be expanding now around the world. We've shipped over 2 megawatts. I think the number is more like 2.5, 2.6 megawatts. We're just starting. And as we scale up the factory, we'll be shipping tens of megawatts a month. Next. So what's so unique about us? The Prussian blue in my background, the blue in the shirt, the Prussian blue on the screen. Prussian blue is a dye. We'll talk a little bit more about it, but it has some very unique properties that allow sodium-ion batteries to do what they do. Next. So what's so unique about us? We have a very large lattice structure. We'll get more into the details coming up in a moment, but the large lattice structure allows us to exchange sodium ions back and forth between cathode and anode with no deformation, no heat, very, very low internal impedance. Next. So we're all familiar with lithium-ion batteries, and before we get any further, let me say this, and I say this in every public forum: there's no such thing as a perfect battery. There's just a battery that's ideal for what you're trying to do, right? So there's going to be a lot of differences here as we go through this. So with a Prussian blue sodium-ion battery, we have a very large cage, no deformation. With lithium-ion, doesn't really matter what chemistry of lithium we have. If we try to jam that lithium ion into a hard carbon anode, we're going to get deformation. We all know that. That's why we have to do forming. We have to do a whole bunch of other things. That's why we need a BMS. It's just the way it is. It all works if you put the right science and technology behind it. Next. So some of the unique properties, because of that very low internal impedance, and because of the way the Prussian blue material works, you can shoot this battery, and we've done that. You can see our safety videos online. You can crush it, you can puncture it, you can light it on fire. It does not burn. It is rated non-flammable by UL. It is rated no thermal runaway by UL, and we're in the process of getting additional agency testing. This is the safest battery that you can buy. Next. Again, if you do a little bit of searching on YouTube, you can look up CNBC sodium ion. It's a very great video. Not only does it address Natron, but it looks at other players, CATL, Hina, Faradion, all that are developing sodium ion chemistries, talks about the differences. More importantly, that is our cell. It's a live cell. In the video, you'll see it fully instrumented. We drill a 25-millimeter hole through that cell, and it keeps on working. Next slide. So again, some of the unique properties, and got a lot of slides, so I'm going to try to speak quickly. Hold there with me. Low internal impedance, 1/4 to 1/10 that of lithium, lead, nickel metal hydride, NiCad. What does that mean? It means you can charge it very, very fast. It means you can also discharge it very, very quickly. So this battery is optimized for very high peak power, very rapid charge and discharge cycles. So you can recharge it in roughly 8 to 10 minutes if you have enough capacity to do that. Next. It operates over a very wide temperature range. I've been involved in many data center builds in Singapore. We all know we're trying to push the temperature envelope. We're trying to, deal with a wide range. Our battery operates from, it's not on the screen, but it technically works from -50, -50 to +50 C. You can charge it and discharge it over that entire range, right? So it's got a very, very, very wide range of operation. Next. So differences, similarities. Very safe, very high peak power. Not energy dense. So if we look at energy, kilowatt hours, we are not as dense as lithium. We're not as dense as other chemistries. We're roughly on par with lead. So we're not going to be something that you put in an electric vehicle. That's not the market we're addressing. We're addressing stationary power applications where you need very high power, very high charge and recharge times, or very fast, I should say, and you're looking for safety, as well as a long life. So much like lithium, where we're seeing now 7 and 10-year lives, sodium ion batteries are going to be 7 to 10-year lives, perhaps even longer, depending on the C rate. Next. So if you go look at our website, you'll see some different charts we have up there available. We look at how we compare again, with nickel metal hydride. There's certainly markets and applications for nickel metal hydride from a sustainability standpoint. We know nickel's not necessarily the best material you want to go dig up out of the ground. Next slide. As well as looking at lithium ion batteries. And again, we're very, very transparent. We are not as energy dense as lithium, but we exceed them on power by a very wide margin. Next. So sustainability. So we talked, I mentioned before, wider temperature operations that we're all trying to do with our data centers, our telecom sites, et cetera. Many of us are seeing now pushes from that ESG, contingent for environment, sustainability, governance. There are no blood minerals. There's no rare earth materials. There's no really long supply chain. We can build the sodium ion battery plant and we can source all the materials on any major continent in the world, except for Antarctica. Nobody can build there. So very, very small compressed supply chain for sodium ion batteries. Next. So some of the products we've already brought out. I mentioned we've got 2.5 megawatts, slightly more out in the field already. Shen has a whole bunch of these in his lab in Singapore. Our what we call our 1U pizza box 4 kilowatt blade server style battery for UPSs and for telecom. Yep, thanks. Appreciate the note there, Shen. So this is a commercial product. It's been on the market now for several years. I can tell you this is public information. T-Mobile designed that and built that into their data centers a couple of years ago for their 48-volt power racks. So again, this product's in the market, UL compliant, for shipping it around the world. Next. So recently, and this is what Shen was talking about, some of the joint development efforts that we've been doing, we launched the Blue Pack. So this takes our core cell chemistry, made our cell larger, made it thicker. We put an awful lot more power into it, put more energy density. We've been shipping prototypes of what we call our Blue Pack, conveniently painted blue. And that is a 25 kilowatt, 48 volt battery, roughly 1.3 kilowatt hours. From that, we can build 480 volt systems, 600 volt systems, 800 volt systems, 1200 volt DC systems. We can gang them in parallel for longer runtime at 48. So there's a lot of flexibility in this. And again, this is what we've been working with Shen and the team at Fuji Brightex on designing a battery cabinet for UPS and other either industrial power or telecom or data center or utility applications. Next. And there you go. There's a picture of a prototype cabinet. This one happens to be sitting in Santa Clara. Shen and his team have almost a carbon copy clone in their data center. Theirs actually has all the bus bars tying all the outputs together. This was taken before. I forgot how old this picture is. This was taken a couple months ago before we wired the whole thing all up. But it's a 250 kilowatt nominal rated battery cabinet. And I'm just going to tell you, when you look at the specs of a Natron battery, because of that low impedance, it's a 350 kilowatt cabinet if you want to discharge it in 30 seconds to a minute. So it's got very, very high capacity available for you. You can also put these in parallel, just like a lead battery or nickel metal hydride or zinc or whatever chemistry you want to go with. So you can put these in parallel, 2 megawatts, 4 megawatts, 6 megawatts. It doesn't really matter. It's all a matter of wire size and how much you can run back to the UPS and your load.
Jack, can I jump in here?
Yes.
So to all that are here, we have moved. We just moved back to our new office in 15 Sinoco Way. The demo room, we have a demo room being set up. We should be ready by the end of September, where we have this demo unit for the Blue packs ready to show you what we can do. Just take note that this battery is high powered, but there's also an advantage, which means it can discharge really fast, but it can charge really fast as well. And I think Jack will bring you to the number of cycles that you can do later on, which is one of our strengths. So please do contact us if you want to see a demo anytime after the end of this month. Thank you.
Yeah. And I just happened to see a question pop up on the screen of if you operate the battery over 50 degrees C. I'll answer on that right now. Nothing. The upper limit is roughly about 65 C. Whole long discussion on what happens after you go above that, but it's not going to explode. It's not going to catch on fire. It's none of that stuff. We just don't recommend running it above that because you start to lose lifetime performance. Sorry, I just saw that one pop up and I thought I'd get that question knocked out. If we can go to the next slide. All right, so sodium-ion batteries. Right, we've been around now a little over 11 years. The first 5 years to 6 years of our life was a lot of, and by the way, I've known Colin since he founded the company, so it was a lot of mad science, frankly, and I'm sure a lot of you are sitting back there going, I've never heard of this, sounds like a science experiment. It was, and it took time to really hone in on what's the materials for the cathode, what's the material for the anode, what's the separator have to look like, what's the form factor, which by the way is a pouch cell. All of those things had to be worked out. After that, we started finding out how do you manufacture it. And we wanted to, and for those who were able to see the video, our CEO, Colin Wessels, was in an existing lithium-ion plant that we're converting over to sodium-ion. We do not need to invent anything new to manufacture this battery, which is very important when you bring a new chemistry to the marketplace. So we brought it to the market. We have UL 1973. We've gone through all the 9548 testing that's available on our website. Shen has all the documentation unredacted. You can have it, read through it at your leisure. This is an incredibly safe battery. So, what are we doing moving forward? As Shen mentioned, we're working on that battery cabinet, preparing to bring that to market. We have the 48 volt 1U boxes already out there. So we'll go on next. Oh, that was a summary. So somehow we got past the, but I'll bring it up here. So some of the applications that we're involved in, we've been deploying these, and that's the bottom picture on the lower right is a real world deployment. That happens to be sitting in Atlanta, Georgia. Those are C plus T inverter rectifiers. This is a 48 volt telecom lineup. We have similar lineups with, and this is public information. We have them with Equinix. They've talked about this on video conferences. They're deployed in their Washington, D.C. data center and using it to provide basically peak power or burst mode power to IT cabinets. Very clever, and it is approved for use, and I said inside the data center, it's inside the white space, right? This battery is so safe, you do not need to change your fire detection, your fire suppression systems, your monitoring systems. You can just put it right in and you're good to go. So it's a very, very successful and very good use for this type of chemistry where you need short duration but instant and frequent use. Yeah, we'll go next. So this is probably not anything that any of you thought of when you came in on this call, but it's very important to understand how batteries can play in decarbonization of diesel and natural gas, how they can play in microgrids. And a very unique property of sodium ion is that fast charge and discharge, the battery doesn't get hot. It actually cools off on recharge. I know you're going to say, Jack, you're nuts. We've got videos on that. You can come to our labs. It's fully instrumented. It cools off as you recharge it. But in these applications where their dynamic loads are very fast and very frequent, our battery can operate 50 to 100,000 cycles. ABB wrote a white paper, presented it at a global conference. Their data and their life test was 97,000 cycles. So 100,000, if depends on how deep a depth of discharge you go. So again, a very unique battery with many applications that we hadn't thought of before. And when we look at microgrids, we look at grid stability, we look at frequency, voltage regulation, we look at bringing renewables on to a grid, right? We all know that there's issues associated with that. And having a battery that can act like a supercapacitor, but for a longer period of time, 30 seconds, a minute, 5 minutes, 10 minutes, on these platforms, we're running 10 to 15 minutes at megawatts of loads. Well, I do talk quickly. Next. What are you doing? So this was I mentioned the Equinix project. That's what the system looks like. So it's a multi-mode inverter rectifier. So we've got a grid tie. We've got the battery. We have a load. And we've got this inverter rectifier that can feed DC, convert it to AC into the load. It can also put AC back to the grid for demand response or peak shaving. But as I said, this is a dynamic system. So if we look at that lineup of breakers at the top of that rack, right, those are 15 amp circuits. Typically the breaker's set for a 12 amp trip. What Equinix is doing is looking at real time at the loads on those breakers, and as it gets up to around 12 amps, they'll inject energy out of the battery, basically downstream of the breaker, so the breaker isn't tripping. So the AC side, if you will, the UPS or the upstream side, doesn't see that load, the breaker doesn't trip, but the IT load is powered, right? It's a very clever concept, and again, this can be deployed right on the data center floor. Next. So where are we today? We've been building these batteries effectively by hand in Southern California. We're scaling up a factory that, for those who saw the video, we're scaling up a factory in Holland, Michigan. That factory will be something on the order of 600 to 700 megawatts worth of capacity. We're in the process of doing site selection for a gigafactory to be announced at a later date. We have contracts in place with Arxada, which is a fine chemical manufacturer in Switzerland, but any fine chemical manufacturer, Pfizer, Dow, you name the fine chemical company, any fine chemical company can make a Prussian blue of the consistency and quality that we need for sodium ion batteries. We bring that Prussian blue into one of our manufacturing plants, in this case in Holland, Michigan. We make the electrodes, we put the electrodes in the cells, we take those out, we put them in the building onto a production line, We make a battery pack. We ship that battery pack around the world. People put it into battery cabinets. They put it into e-houses and e-shelters and whatever you need to do with it to use it into your application. So that plant is going online over the next couple of months, and full volume production begins Q1 of next year. Next. There we go. And I haven't even had any coffee in the last 4 hours. That's
thank you, Jack. Thank you, Jack.
Thank you.
That was well, it was fast. It was really quick. I hope our audience managed to capture all that. We have some very good questions. Yeah. Okay. Wow. Okay.
Yeah.
We have addressed some questions on the chat, and you can take a look at the chat to see whether you get the answers. If not, please do write in to us, to any one of us, and we'll try to answer you as best as we can. Some of these questions are quite challenging because we don't have all the data. But Brian, I'll let you check in with Jack on these questions so that we can address. Anyone who has any questions, please put it in the chat and we'll address it again. Thank you.
Yeah.
So Jack, it's Brian. I've been trying to consolidate some of the questions that are in chat. We've had a couple of questions about can you address what our anode and cathode are made from that makes us unique, and then describe a little bit about our electrolyte, please.
Sure. Yeah, I saw those. So they are Prussian blue analogs, which means they're Prussian blue both for cathode and anode. And we all know from chemistry and science and physics, right? If there's no differential between the two electrodes, nothing's going to flow. So how'd you do that? Well, the anode is a manganese oxide, and the cathode is an iron oxide. So we have a 1 valence electron differential between the two, depending upon the state of charge. We have, by the way, a white paper that is just about ready to be released. Brian and I have the final rev. So I believe by the time I come over to Singapore, we will have that document released. Shen will have it available on his website. We'll have it in digital format. But it's the theory of operation. How does a sodium ion cell work? So it was a great question. And it's manganese oxide, iron oxide are the two real constituents that make the difference between the cathode and the anode. Cell operating voltage, maximum voltage float. So it's different than lithium, right? One of the reasons why we don't have the energy density of lithium is we don't have the cell voltage of lithium. So pouch to pouch, same size pouch, they're operating at 3.6 volts. We're operating at 1.8. I mean, you just do the math. It's like, well, it's got to be half as much energy on the good day. And then when you realize that sodium ions are much larger than lithium ions, there are fewer sodium ions available in the pouch than there would be lithium ion in the pouch. So there is even a lower energy density. So what makes it so different? Again, that Prussian blue, we can get the charge and we can get the power out very fast. So even though there's less energy, we can take it out very, very quickly, and we can put it back quickly. Separator was one of the questions. Separator is identical to most lithium ion chemistries. So we buy the same separator. It's not a real big deal. Electrolyte, I think it's a organic slurry. It's really a paste. And when we make the pouch, one of the reasons why we can drill that hole in it, if you recall the driller, we can shoot it. So when we make that pouch, the electrolyte gets, for all intents and purposes, wholly absorbed within the cell. And it makes the cell really rock hard. Bear with me 1 second, because that was a great question. I'm going to reach into my closet, pull out a cell. That is a pouch cell, hard to see. Pouch cell, you can hear it. Okay, it's not prismatic, but it looks and feels like it's prismatic because that electrolyte is absorbed within the electrodes. I forgot I had that sitting like right next to me, so that was convenient.
Jack, we had another question about what kind of, if any, off-gassing occurs at high temperature.
Great question. So in the UL report is the list of off-gassing. So the primary gases you're going to get, hydrogen. I mean, that's just like, say like anything else. We got plastic in here. We have an organic electrolyte. So once you get it up to temperature, you get the vast majority of it is hydrogen. There's not a lot So you got to realize that volumetrically, the amount of gas we release compared to a lithium or nickel metal hydride or nitride battery is significantly less volumetrically, and most of the volume is hydrogen. You look through the report, you will see cyanide, HCN, is released. It is released at concentration levels typically lower than any agency and any AHJ has got for permitting. If you get to that temperature, by the way, so we've got white papers and Shen has those. We have them on our website. We've got third-party independent safety reports on our battery that say, if you have gotten that battery hot enough to release any of those gases, okay, you've got a bigger problem to worry about because your building's on fire and you're at about 400 degrees C, 500 degrees C before it gets to that point. So again, it's a very safe battery. Great question. All that information is available. We have no issue giving it all out to you. You can go to any fire marshal, any safety agency, and let them read through our data.
Jack, there was a question that Shen addressed already about will Natron battery cabinets be available for multiple or different UPS voltages and with split bus or center tap, and obviously I know the answer to that, but Shen basically said yes, but if you could expand upon that a little bit. And then the follow-on question is, what type of monitoring do we have?
Great question, both of them. So voltages, our Natron right now is focused on designing a 480 volt battery cabinet, single bus, split bus, right? So 480 volt, line to neutral, 240, center tap, for 480. So you've got both configurations available. Shen and his team can make a cabinet for you either way you want. We've designed for the oil and gas world, they operate at 800 volts. So it's basically a 672 nominal voltage, floats at about 812 system. For wafer fab people, they're running at a higher voltage, so they're running at 1200 to 1500. We're doing a center tap, two 750s, two cabinets, both at 750, one floating above the other for 1500 volt string. So there's a lot of different ways to get there. In terms of the BMS, couple things. Our BMS is what we call passive active. Because of the safety of the battery, when we're on discharge, we do nothing. I mean, we're monitoring the temperature, but we don't need to do anything. We don't have to, there are no FETs to control because the battery will not go into thermal runaway. So we don't have to worry about protective circuitry in the event of, because it just cannot physically happen, period. Laws of science won't let it happen. So what do? On recharge, we're looking at cell balancing, where we are balancing cells actively. Again, we're looking at temperature profile. We're getting information that allows us to give a predictive state of health, give you a state of charge. That information is currently Modbus TCP/IP. We serve that up to a host client who then can give that to you over to the UPS and whatever protocol you want, SNMP, right? So it's a very straightforward BMS system, and again, we just give the information to whatever client needs it.
Jack, can you address our first cycle or round trip efficiency, please?
Sure, that's another great question. That low internal impedance gives us a very high efficiency. It's 99% coulombic, 98.5% basically on an energy level basis, electrical energy level. So consider 98.5 to 99% round trip energy efficiency on a 1C. That's where everybody rates, by the way, a 1C charge, 1C discharge. Right. So if you build a 100 kilowatt hour battery with our battery, discharged it over 1 hour, recharged it in 1 hour. Couple things. One, when you're done recharging, it's good to go. There is no settling. There's no cool down period with the sodium ion battery. Once it's charged, you can discharge it. When you discharge it, you can get 100% of the rated energy out of that battery. 100%, not 80 to 20. There's no guard bands. 100%. You take it all. You can discharge the battery, and you guys are going to think I'm crazy. Go read the UL report. It's right in the UL. You can take the battery to 0 volts. Right now, we're not going to recommend you do that. Shen and his team tried doing it, and we had to really do a lot of exercise to get that battery back up. But you can safely take a battery cell down to 0 volts and bring it back, and it does not impact the life, availability, or the performance of the cell.
Jack, I know we're running short on time, but we just had a great question. I'm trying to keep up here. I know it was on an earlier slide, but could you restate what our cycle life is?
Yeah, so we say the minimum rated cycle life is 50,000 hours. I'm sorry, 50,000 cycles, not hours. 50,000 cycles. That's a full 100% charge and discharge. If you're doing less than 100%, we normally expect 100,000 cycles, perhaps even more. It's all going to depend on the depth of discharge and temperature. I mean, it's like any other battery. It prefers to be kept at around 25, 27 degrees C. If you can keep it there, it's going to live a real long time.
Jack, is there any data available for expected residual power after, say, a 10-year lifespan of the battery?
Yes, we are putting that together right now. It's not printed. What we find is that we're expecting 70% roughly at the end of 10 years, 70-75% of the 1C rating. So there could be a good second life for the sodium-ion batteries because unlike lithium, we don't have a hard roll-off on the 1C characteristics. That's pretty linear down to about 40%. So if you've used it at a data center and you've got it, 10 years, you could take it out and go put it in a grid-connected energy storage system and probably run it for another 5 years.
Jack, there have been a number of additional questions and comments about off-gassing. And I think it's important to state that there is not any off-gassing during normal operation.
Correct. This is a hermetically sealed pouch. Someone asked about what runs above 50 degrees C. Once you get up to 85 degrees C, this pouch is expanded to the point where it could open up. We don't like that. Nobody likes an open cell. So that's why we put a limit internally. Once the battery hits 65 C, we do open up a circuit, or we send out a signal to the UPS saying battery's getting a bit too warm. But we do not outgas under normal operations. You have to create a tremendous amount of heat. As I said, it's somewhere around 400 degrees C, 350, 400 degrees C. I'm not the fire expert on that, but it's got to get really hot before that battery will outgas. And again, please keep sending in the questions. I will be in Singapore in roughly 4 weeks, and I'd be glad to meet with you, talk to you. We can look at batteries together. I can show you some of the videos from our labs on some of the test data and what have you. I mean, your questions are awesome. I really appreciate the time that you are putting into asking these questions.
There's been a couple of additional questions, again, on the subject of gassing or short circuiting. Is there any decomposition or internal short circuits that could lead to off gassing?
No. So unlike other chemistries, there's no dendrite formation under any condition. So we don't have a pathway to puncturing a cell internally by itself. It has to be an external force. There's no internal chemical or physical property, overcharge, undercharge, under discharge, deep discharge, freezing it. As I said, it operates minus 50 to plus 50. So none of that happens. Not possible.
One person is asking to confirm that dendrites do not accumulate in sodium-ion batteries.
There's no pathway to form dendrites. There is no expansion or contraction in charge or discharge. Right? We are not forcing anything into a hard carbon anode or cathode. So the cathode and anode materials are larger physically than the sodium ions that are going in and out of them. So intercalation of ions is done with no resistance, effectively.
Jack, there's a question for recommended fire suppression methods. I think this is a big question. Can you help with that?
I'm sorry, what's that?
Recommended fire suppression. So
yes. Okay, so whatever you are using in your data center today, you can use for a sodium-ion battery. It does not require any unique fire suppression systems. If you're using pre-charge active water systems, keep using it. If you're using a gaseous system, use it. There is nothing required unique for a sodium-ion battery.
Before I type it out, so for fire suppression, in short, we do in a comparative context, we do not need any gas. We can use a normal carbon dioxide or dry chemical fire extinguisher, because you're not putting out a fire by the battery, you're putting out a fire by the materials that caught fire surrounding the battery. So electrical fire would be dry chemical, and maybe some other fires like metals and material fire will require carbon dioxide. So I hope that answers the fire suppression question.
So any ABC rated fire extinguisher can be used on a sodium-ion battery fire.
We have a question. We have a question. Sorry, Brian. Just gonna jump in. So sorry. There's a question. Do you use aluminum foil for anode?
Yes. So the anode cathode material is aluminum foil. That is correct. That's how the electrodes are manufactured. So we're plating Prussian blue on aluminum.
Jack, there's a question about what happens upon overcharging, and it might be useful to talk about how low we can go in voltage and recharge as well.
Yeah, so the 48-volt battery has a safe rating up to over 80 volts. So that's typically where we run the battery up for overcharge. If you take it too far, like if you took a 480-volt cabinet and you put 1,000 volts, DC charge into it, you're going to cause one or more of the cells to open up. That's what it's going to do. It's going to physically manifest itself by opening up. Your battery's no good. I mean, it's the same thing as if you had a lead acid jar open up. The difference is we don't have a liquid electrolyte, so nothing's leaking out to cause a containment or a spill or a hazard. But the cell is going to open up, and it's no longer a viable cell. That's what happens on a significant overcharge for a long duration.
Yes, just a question. Do we have a booth in Data Center World? Yeah, I just want to sell this a little bit. Yeah, we do have a booth in Data Center World together with our parent, with Fuji Electric. We'll be at Nifong booth R50. We'll be there from October 11 to 12. Both Natron, Jack, and Brian, Natron, Jack, and myself, and our whole team will be there to answer the questions. We also have the demo units there to show you what the battery looks like, and it will be a working demo. So there'll be a possibility to charge and discharge on site to show you how fast the battery will work. So we do hope to come and join us from October to 11 to 12 at DCW at booth R50. If there are no other questions, please feel free. We will give it another 2 minutes or so. We thank you for your time this morning to join us. If you feel that you have still some other questions coming on later on, please feel free to email us at info@bridex.fujielectric.com. If not, you can just search for us on the website. We are there. And any other things that you would like to ask us, and especially for the demo, please do write to us and we'll try to arrange. Okay, so we thank you for your time. I think more or less we have answered, except one more, the flame-proof enclosure required. No, we do not require any flame-proof. It's actually hard to catch fire. We do have a video online. It's been circulating for some time. It's available on YouTube as well as on our website. You see the batteries put under severe abuse, nail penetration tests, being fired at by a bullet. There's a drill saw test, and the battery still runs. We can even cut the battery, and the battery will still provide a voltage. So that's the safety of the battery that we can attest to. Many are asking about the comparisons with lithium. I think at this point, we need to understand that this is a power dense battery. So for a 5-minute duration or lower, yeah, we're very, very comparable. Anything more than that, for critical backup is great. But anything more than that, of course, there are some disadvantages that we will face, but there's some advantages that we have as well. Therefore, for this more in-depth application questions, please do write to us so that we can do a comparative analysis, a quick one for you. Do take note that we can operate at a wide temperature. When we say operate, means literally we do not need any air-conditioned environment to operate the batteries. The heat release is very, very low, even at boost charge, and it still works at 100% with the same efficiencies. We don't have to manage it. So I think the next question a lot of us will ask will be warranties issues, right? Oh, yeah, your battery can operate high. Yeah, we can discuss that in further detail as well if you do have an application. So do write to us for this, because I cannot give you something outhand right now, but I wish to be able to address this case-to-case basis, but we definitely can. So if there's no other questions, we hope to see you in DCW in October 11 and 12, and looking forward looking forward to see you guys, because there's no faces here in the seminar, just our face, and hopefully we'll see you there. Okay, thank you very much, Natron, Jack, and Brian.
Thank you.
And thank you, my team, very much for putting this together. So
thanks to your team.
Thank you very much,
Yes.
and thank you for joining us.
Thank you.